Dear students, a warm welcome to the lecture series on theory of equations. In this lecture, I wish to explain the fundamentals of theory of equations. In mathematics, the theory of equation comprises a major part of traditional algebra. The theory of equations plays a vital role in other branches of mathematics, including differential calculus. In this lecture, I would like to explain the fundamental theorem of algebra and one subsequent theorem. First of all, I wish to explain what is a polynomial function. A polynomial function of degree n is a function of the form f of x is equal to a0 x raised to n plus a1 x raised to n minus 1 plus etc. plus an, where the leading coefficient a0 not equal to 0 and n is a non-negative integer. Here a0, a1, etc. an, in general ai, are fixed complex numbers, and these numbers a0, a1, etc. an are called coefficients of this polynomial function f of x. Suppose alpha is a complex number such that f of alpha equal to 0, then alpha is called 0 of the polynomial, sometimes root of the polynomial. Next we can look the statement of the fundamental theorem of algebra. The fundamental theorem of algebra states that every polynomial function of degree n greater than or equal to 1 has at least one zero. The proof of the fundamental theorem of algebra is beyond our scope. That's why I am moving to the subsequent theorem. So let us explain the first theorem in this regard. The first theorem states that every polynomial of degree n has n and only n zeros. That is, the theorem states that every polynomial of degree n has n zeros and it has only n zeros. The two things we have to prove in this theorem. Now let us discuss the proof of the theorem. Consider a polynomial function f of x is equal to a0 x raised to n plus a1 x raised to n minus 1 plus etc. plus an. Here we are considering a0 not equal to 0. Then only we can assure that it is a polynomial function of degree n. And suppose the degree n greater than or equal to 1. Then by the fundamental theorem of algebra, we have f of x has at least one zero. Suppose alpha 1 be the zero of this polynomial. Then as we know, if alpha 1 is a 0 of a polynomial, then x minus alpha 1 must be a factor of this polynomial. So we can express f of x is equal to x minus alpha 1 into some q1 of x, where q1 of x is another polynomial of degree n minus 1. Here the degree of this polynomial function f of x was n, and the degree of this factor, this is a linear factor, therefore the degree of this linear factor is 1. That's why the degree of this q1 of x is n minus 1. Then again, by the fundamental theorem of algebra, if this n minus 1 greater than or equal to 1, then this q1 of x has at least one 0. Let it be alpha 2. Then q1 of x has a factor x minus alpha 2. Therefore q1 of x can be written as x minus alpha 2 into q2 of x for some q2 of x. Then f of x can be written as x minus alpha 1 into x minus alpha 2 into q2 of x. Here the degree of this q2 of x will be n minus 2, because there are two factors, x minus alpha 1 and x minus alpha 2, and their product will constitute a polynomial with degree 2. Here the degree of f of x was n, therefore degree of q2 of x is n minus 2. Now we can repeat this process. Then at some stage we will reach f of x is equal to x minus alpha 1 into x minus alpha 2 into etc. x minus alpha n into qn of x, where qn of x is a polynomial of degree n minus n, that is equal to 0, because we have taken n factors outside, x minus alpha 1, x minus alpha 2, etc. x minus alpha n. The degree of a polynomial equal to 0 means it's a constant. Therefore qn of x is a constant. Now by considering the right hand side of this expression, if we are expanding the product of these n factors, the leading term will be x raised to n, and the coefficient of that leading term will be qn of x. But at the beginning we were taken the polynomial f of x as a0 into x raised to n. Here the coefficient of x raised to n was a0. Therefore qn of x will be equal to a0. Therefore we can write f of x is equal to a0 into x minus alpha 1 into x minus alpha 2 into etc. x minus alpha n. Here alpha 1 is 1 0, alpha 2 is another 0, etc. alpha n is another 0. Therefore this polynomial function f of x has n zeros. Now we have to prove the second part, that is the polynomial function f of x has only n zeros. For that one, suppose we are taking alpha as a number other than alpha 1, alpha 2, etc., alpha n, then we can say that f of alpha not equal to 0, because by putting alpha on the right hand side of this expression, no terms will be 0, because alpha not equal to alpha 1, therefore alpha minus alpha 1 not equal to 0. Likewise, alpha minus alpha 2 not equal to 0, etc. Alpha minus alpha n not equal to 0. Therefore, any term on this right hand side will not be 0. Therefore, we can conclude that f of alpha not equal to 0. F of alpha not equal to 0 means that alpha is not a 0 of this polynomial f of x. So, if we take alpha as a number other than alpha 1, alpha 2, etc., alpha n, then we have obtained that alpha is not a 0 of this f of x. Therefore, we can conclude that any number other than alpha 1, alpha 2, etc., alpha n will not be a 0 of this polynomial function f of x. That means f of x has n roots and f of x has only n roots or only n zeros, namely alpha 1, alpha 2, etc., alpha n. So we will discuss the subsequent results in the later lectures. So thank you very much.